So now I'll go over the problems for levels 3 and 4. So first of all, level 3. So let A, B, C, D, E, and F be integers selected from 1 to 100 uniformly and at random with replacement. And so then let M be equal to A plus 2B plus 4C plus 8D plus 6E plus 32F. And so we want to find the expected value of the remainder when M is divided by 64. So what we can do is consider M mod 64 in binary. And so in binary, M mod 64 has a total of 6 digits. And so one way we can think of M is basically to basically first let M be equal to 0, and then A gets added to M, and then 2B gets added to M, then 4C gets added to M, then 8D gets added to M, then 16E gets added to M, and then 32F gets added to M. And so after A gets added to M, then this is the only term in the sum of M that can affect the remainder when M is that can affect the final digits. And so it's random from 1 to 100. So there's a 1/2 chance that the rightmost digit will always be 0, and a 1/2 chance that it will always be 1. And so now let's look at 2B. So 2B will not affect the last digits, and it's the only digit sum of these 4 that apart from A. So we basically just ignore all of the ones that we've already included. So 2B is now the only number that can affect this digit. And so there's a 1/2 chance that it's 0 and a 1/2 chance that it's 1. And so now we can ignore. So 4C, so using 4C, we can ignore these 2 digits. And so now 4C is the only digit left that can affect the third from the right digit. And so using that, there's a 1/2 chance that it's 0 and a 1/2 chance that it's 1. And so now 8D. So now 8D can only affect this digits and the digits to the left. And since 16E and 32F can only affect these 2 digits, that means that 8D is the only digit left that can affect this digit, which is the third from the left digit. And so there's a 1/2 chance that that digit is 0 and a 1/2 chance that it's 1. And so for 16E, once again, it can affect this digit, and 32F here can only affect this digit, and so that means that 16E is the only number left that can affect this digit. And so there's a 1/2 chance that that digit is 0 and a 1/2 chance that it's 1. And so finally, 32F can only affect this digit. And so once again, it's 1 to 100, so it's 50-50 whether the number is even or odd. And so there's a 1/2 chance it's 0 and a 1/2 chance that it's 1. And so that means that and so what that means is that M mod 64 has each digit as 0 or 1, and this is equally likely. And so And what that means is that 0 to 63 mod 64 is all equally likely. And so what that means is that the expected value, where I'll just abbreviate as EV, is equal to 63 times 64 over 2, which is the sum of 0 to 63 divided by 64, which is the total number of numbers from 0 to 63. And this is equal to 63 over 2. And so now let's move on to the level 4 question. So let k be a positive integer. And so there are two players, A and B, playing a game on an infinite grid of regular hexagons. And so initially all grid cells are empty. And so the players alternatively take turns with A going first. And in his move, A can choose any two adjacent hexagons that are empty and place a rock in both. And now in B's move, you can choose any rock and take it away. And if at any time there are k consecutive grid cells in a line, and all of them have a rock, then A wins. And there is no win condition for B. And so we want to find the minimum value of k such that A cannot win in a finite number of moves. Or we can prove that no such minimum value exists. And so, first of all, we can arrange the board such that it looks something like this. So it looks something like this. Okay, I'm aware that these are not quite regular hexagons, but they are roughly regular hexagons. Okay, yeah. And so, and now we can create a coordinate system. And so we can let this be 0, 0. And so then we can use this to be referred to as this is 0, 1, and this is 1, 0. And then so that would mean that, sorry. And so that would mean that this would be 1, negative 1, and so on. Okay. And so what that means here is that 2 would touch 2 hexagons, touch if the coordinate difference is equal to 1. And so now we can claim that, okay, so claim the answer is k equals 6. And so what we first need to do is show that k equals 5 fails. And if k equals 5 fails, if k equals 5 is a win for A in a finite number of moves, then we can see that k less than 5 also will be failed. If k equals 5 fails, then k is less than 5 would also fail. And so now we can just do the case of k equals 5. And so now, for when k equals 5, we can just let a, and so then we can let him only place in the hexagons that correspond to, oops, that's not if, that should be in. A should place in the hexagons with an x coordinate in 0, 1, 2, 3, 4. X is in this, and y is 0 or 1. So now in A's turn, if there are 4 counters in either row, then obviously A wins immediately. And so now assume that each row has at least 2 missing. And so that means that at most 6 counters are on the board. And so we want to find when A can't play under these cases. And so first of all, we can look at the disjoint sets. Let me scroll down a bit. Okay. So look at the disjoint sets 0, 0, 0, 1, 1, 0, and 1, 1, 2, 0, 2, 1. And finally, the third disjoint set is 3, 0, 3, 0, 3, 1, 4, 0, and the final disjoint set would be 4, 1. And so now we can see that each set either has at least 2 hexagons without counters, and then A can move, and then A can make a move in that set, or all 4 have exactly one missing. And so we can do the exact same for another different group of these sets, which would be 0, 0, and then 0, 1, 1, 0, and 1, 1, and 2, 0, 2, 1, and 3, 0, and finally 3, 1, 4, 0, and 4, 1. And so now we're assuming here that A cannot make a move, so clearly all 4 have exactly 1 missing in both of these groups, in both of these sets of sets. And so what that means is that 0, 0 and 4, 1 are both empty. And so what that means is that it must be true that 0, 1 1, 0, 3, 1, oops, not 10, 0, 1, 0, 3, 1, and 4, 0 do. And so what that means now, not all of these, but some of these do. And so what that means now is that 3, 0 and 1, 1 are also empty. And so this is the only situation in which A cannot win, and he cannot play in any of the hexagons, any of the 10 hexagons. And so now the strategy from here is A only plays in these 10 until he can't. Sorry, until he either wins or cannot move. And if he wins, then we're already done. And so, however, if he cannot move, then we've already figured out what the grid situation would look like up here. And so now A can play in the hexagons 5, 0 and 5, 1. And so if B takes 5, 1, then A could win at 2, 0. And if B takes away 5, 0, then A can play at 5, 0 and 4, 1. And when he does this, then afterwards he can play at 3, 0 and or 1, 1 the next turn. Either that, or if B removes something from this set earlier, please wait. If B removes something from this set, then A either wins immediately. If B takes from sets up there, I'll just refer to this as S. And so if B takes from set S up there, then what that means is that A can either win immediately, or he can either win immediately at 3, 0, or he can just play in both columns. Or rows, and he can win in the next turn, because B can no longer block both at once. And so now we can do the case of, and so now we can take the case of K is, that's too cool. I'll just move the color. So if K is at least 6, then A can play on anything. A can just play on the lattice. A can play on the hexagon that get generated by 2, -1 and 1, 1. And what that means is basically he can play on the points that have coordinates of the form 2a plus b, comma b minus a for integers a, b. And then b removes it. And otherwise, if b removes any of a's counters. And so this works because in order for a to win, then for a to win, there needs to be at least 2 counters on the lattice. But since B always removes any counters that are of the form this, and he can only place one of them at a time, So then A has at most one counter on this lattice at all times. But he needs at least two, and so A cannot win. And so that means that A can only win if K is at most 5. And so the answer to here is the minimum value for which A cannot win in a finite number of moves is 6.